Yeah, that's very nice. Okay. Uh, so so okay, so we can continue. so so these confidence intervals, they just like all frequentist methods, they refer to all thinkable data, and they actually say nothing of consequence about the actual data that you have observed. By contrast, the Bayesian credible interval makes a definite statement about the actual data and only about them. Okay, so you don't care about other data that could have been observed but was not observed. So let me give an example of how confidence intervals and credible intervals are different. And I'm using a very nice example that I believe was invented by Edwin James. So that's the same Janes of the Janes-Cummings model in quantum optics. And he thinks of the following situation. So there's a certain process that runs well up to a time capital T and then starts to fail at a rate R. And the probability of the failure occurs between T and dt is given by, well, the dt, and then there's the rate, an exponential decay, and a step function that says that, well, it runs okay up to time T, and then failure sets in, okay? And we want to estimate the capital T from the data. So we take 3 measurements, and we observe a failure at time t1, which is 10 units of r, a failure of time t2, which is 12 units of r, and a failure at time t3, which is 15 units of r. And so you can ask now, what is the 95% confidence interval for the quantity that we want to determine? And what is the 95% credible interval? Okay, so if you look at the standard answers, then the standard confidence interval is bound by 10.2 and 12.2 units of R. And the smallest credible interval is bound by 9 and 10 units of R. Now, remember that we had observations at 10, 12, and 15 units of R. So the true value of T is certainly not more than 10. And so it follows that the confidence interval does certainly not contain the actual value. Okay, so you're applying these methods and you get something that clearly violates common sense. Now, there's nothing wrong with how these confidence intervals are constructed. It is just that the confidence interval that is associated with these data tells you nothing that is useful. Okay. Now, if you look at the smallest credible interval, I mean, that is in the range that is clearly reasonable for the data that you have observed. So it's between 9 and 10, and that makes perfect sense. So if you never saw an example where you see a clear difference between the two, here you have one. So if you want to read more about this, there is this archive paper by a certain van der Plas that talks about what Janes did in '76, and then we have elaborated on it in one of the appendixes of the papers that came out of my group published in 2016. Now, what about hypothesis testing? Okay, so p-values. So here is a citation from this nice book by Diaconis and Skirms, 10 Great Ideas About Chance, published by Princeton University Press in 2018. It's really an enjoyable book that I recommend to all of you. And so what do they say? Under the section, why most published research findings are false, they say, a cookbook frequentist hypothesis tester doesn't have to think. He calculates a p-value. That is defined as the probability that random noise would generate a false positive. And then they reproduce a cartoon that they had been around for many years already, but if you haven't seen it, I will show it to you. If you have seen it, you will enjoy it again. So it's a question of whether the sun just exploded. It's night, so we are not sure. We don't see the sun. So here we have a neutrino detector, and the neutrino detector measures whether the sun has gone nova. And then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it will the truth. It will tell the truth. So now, oh boy, the detector has gone off. So the sun has gone nova, right? So let's look at this, what the frequencies would say. The frequency says the probability that this result happens by chance, well, that comes from rolling the two dice, is 1 divided by 36. That's 2.7%. That's below the threshold of 5% for what is the customary thing for p-values. And so I conclude that the sun has exploded. The Bayesian statistician is a bit skeptic and he offers a $50 bet. Okay. So now what about hypothesis testing by p-values? Some years ago, statisticians started to worry about the p-values and the abuse of p-values in much of the published literature. The things that worried them most is p-values used to in medical data, evaluating of medical data, drug tests, and so forth. And so they have a list of observations, and I just want to draw your attention to point 4, where they say that proper inference requires full reporting and transparency. You should be wondering why it is even necessary to state that. Okay. I mean, this is just saying that you have to be honest. And then also under point 5, they note that the p-value of statistical significance does not measure the size of an effect or importance of a result. And they go on to say that by itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. And if you want to see more about that, then of course there was a reaction by Benjamin and 71 co-authors published in Nature Human Behavior 2017. So this was after that, where they suggest that one redefines statistical significance, but it's just using a different version of p-values. And then Amrine, Greenland, and Shane, and more than 800 signatories argued in Nature that one should retire statistical significance. But the therapy that they offer for this kind of problem is really to kind of review these methods and do something different but similar. And then at about the same time, somebody suggested that maybe we should set the threshold at 0.5% rather than 5%. Because the 5%, that's a historical number that goes back to days when we didn't have a lot of data and powerful computers. So, but again, I mean, that's not really solving any problem. Now, what about physics? Okay. So I'm reminding you of 4 experiments of some 5-6 years ago, at the time when this discussion happened. The 4 experiments that were reporting loophole-free Bell inequality violation, Bell inequality tests, and all of them try to make their case by reporting a p-value. So Delft people reported a p-value of about 0.04, which is just below the 5% threshold. The Vienna experiment claimed a p-value of 10 to minus 31. That number is so small that again you should kind of wonder what it really means. Boulder experiment had a p-value of 10 to minus 7. The Munich experiment had a p-value of 10 to minus 9. So the Delft experiment, the Munich experiment are very similar. The main difference is that the Munich experiment had 100 times more data than the Delft experiment. And the Vienna and the Boulder experiment are also very similar. The Vienna experiment had more data than the Boulder experiment. So having more data is clearly reducing your p-value. Okay, so let's just look at this from a different point of view. And so namely from the Bayesian perspective. So we will look at the data from these experiments, but apply a different notion of evidence. And so let me explain what that is. So in the Bayesian data evaluation, every possible outcome has a prior probability, which just summarizes what you know about the situation before you take any data. Then you take your data, and then with the data taken into account, every possible outcome has a new probability assigned to it because you have learned something. Okay, it's just like weather forecasts. You look out the window and the sky is blue, and then you don't expect it to rain in the next half hour. You look again and you see dark clouds, you adjust your probability for having rain in the next half hour. Okay, same here. So we have prior probabilities for the events. We take data, we make adjustments that take into account what we learned from the data. Now, if you look at case one, the posterior probability is larger than the prior probability, and the same for case two. Whereas for case three, the posterior probability is less than the prior probability. In this situation, we say that the data provide evidence in favor of cases one and two and against case three. It's as simple as that. Now you can even quantify that, whether the evidence is weak or strong, but we don't need that today. So let me just accept this as what we call data gives evidence in favor and data gives evidence against. Then from this simple concept of evidence, you can actually construct a whole theory of statistics. And if you want to see how that is done, look at Mike Evans's book of 2015. So now in these experiments, we want to distinguish quantum mechanics from little local hidden variable theories. And so if you look at the data, you can interpret the data with quantum mechanics. And so you use quantum mechanical probabilities to talk about the data. And so the quantum mechanical probabilities in the probability simplex occupy a certain portion of the simplex, here indicated by this ellipse. But now you can also invoke the local hidden variable description that gives you a different set of probabilities. They occupy a different portion of the probability simplex, here symbolized by this triangle. And then there is an overlap region where you have probabilities that could derive from quantum mechanics or could derive from the local hidden variables. So now the question is, for these three regions, do the data provide evidence in favor or against each of the three subsets of probabilities? And so this is the question that we are asking, and we see what the data tell us. So now I have to say something about how this is done. So in this Bayesian procedure, we have four ingredients: the data, right, denoted by D. Then the prior probabilities that we associate for the parameters. Then there is the likelihood, which is the probability that you observe the data given the values of the parameters. So this is a conditional probability for the data, conditioned on the values of the parameters. And then there is the posterior probability distribution, which you essentially get by multiplying the prior with the likelihood and normalizing, but I don't write the normalization factor. Right. And then what is very important, that you must have ways of checking all the ingredients against the data. So we have to ask, are the data typical? For that, we have so-called run tests and checks for prior data conflicts. And the question is the model correct? I mean, the way how we calculate probabilities for the given situation. Are we doing the right thing? And if necessary, we have to do a model checking. You will see an example of that. And the other question is, do we have a bias in our prior, in the way we assign the prior probabilities? And so there are tests for and against bias. Okay, so we make sure that there is no bias. Again, you will see an example for that. So now let me say a little bit more about the experiments. So all these experiments measure coincidence events on qubit pairs. So they all have a source of qubit pairs and a trigger that tells the source to produce a pair. And there's a probability gamma for the conversion. So not every trigger signal may actually produce a pair. And then of the pair, one of the objects goes to Alice and one of the objects goes to Bob. And Alice has sort of a filter that lets the particles go through or not. Bob has also a filter, lets the particles go through or not. This filter is characterized by by a setting for which we use vectors A and A prime for Alice and B prime for Bob. And then there's a detector that receives the particle and clicks or doesn't click. And then these detectors have finite efficiencies denoted by eta A and eta B for Alice's detector and Bob's detector. And in each event, for each trigger event, we either have a click on both sides, that's a coincidence event, or we have a click only on Alice's side, that's an Alice only event, or we have a click only on Bob's side, that's a Bob only event, or we have no click at all. We have a trigger signal, but we have no clicks at all. So that's a null event or no detection. And so all these experiments are characterized by telling you what is gamma, this probability for the conversion, the settings, or actually more important, the angle between the two vectors, and the same for Bob, the angle between the two vectors, and the detection efficiencies on both sides. And then for each setting, so there's a setting A, B, setting A prime, B prime, A, B prime, and so forth, A prime, B prime. So for each of the setting, we have 4 probabilities. 1 probability for the coincidence events and for the other 3 also. Okay, so we have 4 settings, and for each setting, we have 4 probabilities. So now let's look at these different experiments. So in the Delft experiment and in the Munich experiment, you had event-ready kind of doing it. So the gamma is 1. You only take data when you know you have a pair. And the angles between the settings is very large, 90 degrees, 80 degrees for Delft, 90 degrees, 90 degrees in Munich. The detection efficiency is also very, very large because you're working with atoms in these experiments. And however, the total number of events is not that large. It's only like 250 for the 2 runs of the Delft experiment. And it's like 27,000, 28,000 for the 2 Munich runs. So it's about a factor of 100 between those. And so this is also one of the reasons why the p-value calculated for the Munich data is so much smaller than the p-value for the Delft data. Now, the Vienna and the Boulder experiment are also similar. Here, the gamma values are very small. Okay, so these are experiments that use down-converted photons and pulsed sources for the pump. The angles are around 60 degrees between the settings, and the detection efficiencies these are single photon detectors. They are just above the threshold that works for these experiments, so somewhat in excess of 70%. And so then for each of these experiments, you have the 4 settings, and for each setting you have 4 event counts. So altogether you have 16 counts of events, and that string of 16 numbers are the data. And then the sum is the total number of trigger signals, and that number is listed in this last column. So you see an enormous difference here. So in the Vienna and Boulder experiments, we have not just millions, but thousands of millions of events. and was in Delft it was just 250, and in Munich it's 28,000. But these experiments are characterized by much larger efficiencies, both on the conversion and on the detection. So the data from the different experiments are quite different. And so now we have the 4 settings, and for each of the settings we have the probabilities. And then you can calculate, say, the probability that detector clicks on Alice's side, and that must not depend on what happens on Bob's side. So those are non-signaling constraints, and they're automatically obeyed by the probabilities that are used both in quantum mechanics and in the local hidden variable description. But since you have these constraints that this sum of probabilities has to be equal to this sum of probabilities and so forth, then you don't really have 16 different probabilities, but you only have 12. First of all, for each of the 4 settings, the 4 probabilities add up to 1, so there are only 3 independent ones, and then you have more constraints here. So in the end, you only have 8 independent variables in the system. So you're actually reducing the last probability simplex to an 8-dimensional hyperplane where all the relevant probabilities reside. And then, so this picture that I showed earlier with the triangle and the ellipse, that's actually a picture that symbolizes sets in this 8-dimensional hyperplane. Okay, so now for the quantum mechanics, I just remind you that we have a statistical operator and we have projectors that select the events. And so for each of the settings of A and B, or A prime and B prime, we can calculate these probabilities and the joint probabilities according to the rules. And so here's the expression for the null events. And so this is for one setting, and you can look at the other settings as analogous expressions. So this is all straightforward, and you just apply your knowledge of how quantum mechanics works. And then there are certain constraints, and we that come from from these expressions. So this probability for coincidences cannot be more than the probability for having a pair, and then the probability of the detectors, the detection probabilities of the two detectors values in Bob. And likewise, you have constraints for the other probabilities that appear in these sets. Okay, and so I remind you that for the Delft and Munich experiments, the gamma is 1, so this is kind of 0, and these detection probabilities are close to 1, and so there are no major portions of this 8-dimensional hyperplanar excluded by these constraints. However, in the Vienna and Boulder experiment, the gamma values are small, and so these constraints exclude big portions. Okay, so we need to pay attention to these details. And so let me just skip this because it's technical. Now for the local hidden variables, there's a general way of how you do that, and that is by just saying that, you have these 16 cases, and for each case you have a probability, and you don't care what's the mechanism, you just assign a probability from a trigger to detection. But you also have these no signaling constraints, and so again you get the same size of the parameter space, and so these probabilities would then be in this symbolic triangle, right? And so now, so the question is, where are we, right? And I also should remind you that for the 4 different experiments with their 4 different sets of parameters, this ellipse and this triangle are really quite different. So it's not one ellipse for all the experiments and one triangle for all the experiments. These parameter sets are quite different. But of course, this is all something that one can control. So now we have a prior probability, and so in the probability space, we have a volume element, which is kind of the differential of all the probabilities, but multiplied by a function that incorporates the constraint. So this function is 1 when the constraints are obeyed, and is 0 if they are not obeyed. So it's a product of delta functions and step functions. Okay, and then if you take any region in the probability space and you integrate with this volume measure, you integrate your prior probability density, you get what we call the size of the region. So that's size in this sense that it measures the prior content of the region. So if we look at the whole space, we get 1 because that's a normalization of the prior, and then you have fractional values for smaller portions of the region. And of course, if I look at this overall thing, then we have the red region, which is the quantum mechanics only region. We have the blue region without the green region, so that's the local hidden variables only. And then we have the green region where we have quantum mechanics or local hidden variables. And the prior contents of these 3 regions, of course, add up to 1 because your probabilities have to be somewhere. Okay. And for the posterior, well, we multiply the prior with the likelihood function. and that will give us an integrate over the region, and that will give us the posterior content of the region, which depends on the data. So that's this number labeled by C, and it stands for credibility. And then there's a normalization factor, which is just the probability for the data, where you integrate the same expression, but over the whole space. Okay. So what's this likelihood function? Well, we have the probabilities. We have the probabilities for the different events. So the probability for observing coincidences, Alice only, Bob only, null events for each of the settings S. And then this is taken to the power of how many events you have. And then there are combinatorial factors, which are less important, but they're also there, which make sure that everything is properly normalized. But anyways, it's a product of probabilities mainly. And for every observed event, you get a factor with the probability for that event. Now, these probabilities depend on the parameters. So the parameters in the quantum description or the parameters in the local hidden variable description. And so those parameters trace out those regions. And so now we go back to the concept of evidence that I explained earlier. And so we have evidence in favor of some region R when the credibility of the region given the data is larger than the size. So if the posterior probability assigned to the region, now that we know the data, is larger than the probability we assigned to that region before we had the data. And there is evidence against if the credibility is smaller than the size. And of course, the posterior contents also have unit sum. So just like the prior contents have unit sum. All right. So now we need to assign a proper Bayesian prior. And by the rules of Bayesian reasoning, the prior should account for everything we know about the experimental situation before we take the data. Now, if we take that rule seriously here, then we would, of course, say, well, we know that quantum mechanics works, okay? And we would assign a huge prior to the red area, maybe a little bit to the green area, but very small prior to the blue area, because we know that local hidden variables don't really work, okay? So if we do that, we would be accused of having choosing a prior that is heavily biased in favor of quantum mechanics and against the local hidden variables. So since we really want to show that quantum mechanics works and the local hidden variables don't, we deliberately violate the rules here, and we choose a prior that treats quantum mechanics and local hidden variables on equal footing. Okay, so the prior, let me just describe it in simple words. Basically, has a lottery which generates, say, 1,000,000 points in the ellipse, and it also generates 1,000,000 points in the triangle. Okay, so rather than having lots of points in the red region and few points over here, we have 1,000,000 points in this example in the blue region and 1,000,000 points in the ellipse. Okay, and so we actually define the prior by a sampling algorithm, but let me not go into this technical detail. So then we have to check the prior for bias. And so let me see, come to this later. So let me just say that we will talk about the priors confirmation, but we basically have to make sure that if we generate mock data from true probabilities in the quantum only region, then it should not do something fancy. And in particular, if we use mock probabilities from the other regions, we should not get evidence in favor of the quantum mechanics only region. So I come to that, I go back to this in a while. And so I'll just talk about this when we get to it, okay? So now let's look at one of the experiments. So here is a run of the Boulder experiment. So this is a run with where they had like 5 trigger signals per trial, and they have hundreds of thousands, millions of trials, and so that's the recorded data. So for the setting AB, They have 6,000 something coincidences and 22,000 null events and 3,000 each for the Alice only, Bob only. And for the other settings, they have other numbers, right? So it's a lot of data. And now remember the likelihood function, the likelihood is probabilities taken to the powers of those numbers. So these probabilities, of course, are all numbers less than 1. You take them to very large powers. You get an actual likelihood for the data that you have observed, which is extremely small. But that's fine because there is a lot of thinkable data. I mean, just imagine that rather than having 6,378 clicks, you could have had 6,377 and one more of the null events. And that's sort of a neighboring set of data. And that will have similar overall probability. So since there is a huge amount of possible outcomes, the probability for each outcome is bound to be small, right? So that's not something that scares us. However, if we look at the data and we evaluate what we find by what I just described to you, then our prior, as you can see here, assigns a very small probability to the quantum mechanics only region and about equal probability to the overlap region and the hidden variables only region. So clearly, we do not favor the quantum mechanics only region by the prior. We look at the data and calculate the posterior. All the probability is in the overlap region. So this would tell us that there is very strong evidence in favor of the overlap region, in favor of the both case. And so the data are inconclusive. They don't tell us whether quantum mechanics is right or the local hidden variables are right. We simply cannot tell. But now remember that the Boulder team who refuted the local hidden variables on the basis, they did this on the basis of a p-value, which was really, really small. So what's going on? So it turns out that if you look at the paper, there's one number in the paper which they haven't actually measured. And that's this conversion probability gamma from the trigger signal to the pair. So they quote a number of 5 times 10 to minus 5, but they don't say where it comes from. And it's the only number given in the paper that doesn't come with an error bar. Okay. So it turned out they hadn't actually measured that. And for their way of evaluating the data, calculating the p-value, it doesn't matter. This number never enters their reasoning. Okay, but it enters our reasoning because it enters the quantum mechanical probabilities. Okay. So if we look at the likelihood and we just look at the likelihood of the data and we use the quantum mechanical probabilities, we find a number which is like 10 to minus 700. I told you that these likelihoods are small numbers. And you look at the likelihoods from the local hidden variable, then it's 10 to minus 40. Okay, so we have a discrepancy of 650 orders of magnitude. Oh, some of you may remember Serge Henot's talk about a few weeks ago, who talked about the greatest discrepancy in physics, where you have a discrepancy of 120 orders of magnitude. We beat this hands down. We have 650 orders of magnitude, okay? However, what this really means is that the actually observed data, if you look at the quantum mechanical number, are extremely untypical. And this should really not happen when you have so many events recorded, because after all, the law of large numbers kicks in if you have so much data. So there is a problem with this reported value of 5 to 10 to minus 4. So we check the model. And in this case, this means that we actually estimate gamma from the data, which we can do. And when we do that, we find a value of gamma, which is not 5 times 10 to minus 4, but more like 7 times 10 to minus 4. I said 10 to minus 5 earlier, 10 to minus 4. So it's 7 times 10 to minus 4. And so it's about 20% larger really than it is. And if we use this number, then the quantum mechanical likelihood is 6 times 10 to minus 29. It's now larger than the likelihood for the hidden variables. So now the data are much more likely for quantum mechanics than they are for local hidden variables. by 11 orders of magnitude. Okay. So, and if we use this value for gamma to go through the analysis, of course, the prior probabilities are as before, but now the posterior is such that all of the posterior values are in the quantum mechanics only region. Okay. So this model testing that we had to do here, I told you that we have to check the ingredients. So we have to check the data, whether the data is typical or untypical. We have to check the properties of the model, and there was a problem here with the model. And we have to check the prior. I'll come to that. Okay. So now let me say a little bit more about this. So if you look at at the value of gamma, then the black line is the so-called maximum likelihood estimate for your likelihood. Okay, so it goes up like this and goes down like this, and so this is so the black curve is the quantum mechanical maximum likelihood estimate, is this kind of value, the likelihood for the quantum mechanics, a maximum of the likelihood. And if you do the same thing for the hidden variables, you just get this constant dashed line. Okay, so if you just look at it from this point of view and calculate p-values, you don't see the sensitivity to this number. So the number given in the Boulder paper is 5 times 10 to minus 4, so that puts us here. But please to note that this value is even outside the region where the estimated probabilities violate the Bell inequality of the Eberhard kind that they are studying. And you can also look at the angle between the probabilities, the estimated probabilities, and the probabilities of the target state, the state that they wanted to make in the experiment. But of course, there are always imperfections. And if you put the gamma value around here, this measure of distance between the two probabilities, the so-called Bhattacharya angle, so that just measures the difference between two probability distributions. Here, the probabilities of the target state and the probabilities estimated from the data. That also is best if you are here. So you can be pretty sure that the true value of gamma is not 5, but is more in this region. And if we operate in this region, then you see that in this region, the quantum mechanical probabilities are somewhat larger than the values for the local hidden probability. So this is the likelihood. Okay, so this is the 10 to minus 40. This is the 10 to minus 700. Okay, on this scale. Right. So this extraction of the value of gamma from the data was really important to get a reliable answer. Now let me talk about checking the prior for bias. So what we do is we choose mock probabilities from the 3 regions, and then we generate data as we simulate the experiment and generate data, and then go through the whole process and see whether we get evidence in favor or evidence against. So if we choose choosing 10,000 mock probabilities, true mock probabilities, or mock true probabilities from the red region, and then we generate data and we evaluate the data, we get evidence in favor of the quantum of the red region in 8,800 cases. In 1,200 cases, we get evidence for the green region. Yeah. Sometimes we get evidence for both, and this is why this number is more than the sum of these two numbers, more than 10,000. Now, if we choose mock true probabilities from the green region, then we get about 8,000 times evidence for the green region and about 1,600 times evidence for the blue region. Yeah, but we never get evidence for the red region. And the same, if the mock true probabilities are chosen from the blue region, we do this 10,000 times, we simulate the experiment, we evaluate the experiment, we get evidence for the blue region most of the time. Sometimes we also get evidence for the overlap region, but we never get evidence for the quantum mechanics only region. So there is a bias in the prior that we are choosing, but the bias is against quantum mechanics. It's not in favor of quantum mechanics. Right. So now what I told you is how we evaluate, what I showed you is the data for one run of the Boulder experiment. So we can also evaluate the other runs of the Boulder experiments and all the runs of the other 3 experiments. And in all cases, we get the same story, namely that there is very strong evidence in favor of quantum mechanics and against local hidden variables from this Bayesian analysis. So what are the take-home messages? So first of all, let's remember that quantum data are statistical in nature, and you knew this already. Now, when you plan an experiment, use these concepts from frequentism where you consider all thinkable data that can happen and plan your experiment accordingly. However, once you have taken the data from the experiment, do rely on Bayesian logic when drawing inference from the actual data, because you can not get any real statements if you use confidence intervals and p-values, okay? And of course, local hidden variables are a lost cause, so that's what these data tell us, and that's of course also not unexpected, right? So I'm closing now by thanking the audience for staying with me till the end, and I also want to thank all the students and colleagues who have contributed to this effort over many years. Thank you.
Thank you, Berge, for very nice talks. We are opening the session for questions now. Who wants to start? So maybe let me start, Berge. So I mean, you know, with the p-value, at least you can somehow have a quantitative knowledge of how far you are from what you want to be, for example. I mean, in your case, I mean, can you have some kind of quantitative estimation at the end? I mean, if you take the example of these 4 experiments, so which experiment is at the end the best one? Can you say something?
Okay, so I don't have a slide about this, but I can just tell you. Okay, so for the Boulder experiment, for all the runs, we have the same picture. So we just have nothing left in outside the quantum mechanics only region, right?
Mm-hmm.
For the same is true for the Vienna experiment and for the Munich experiment. For the Delft experiment, that's the experiment with the fewest data, right? And the smallest p-value, okay? You still have a posterior probability for quantum mechanics only, which is very close to 1, but these 2 probabilities are not 0. Okay, so even in that case, you have strong evidence in favor of quantum mechanics only, but maybe not quite as strong as in the other cases, but certainly much stronger than the p-value of 0.039 suggests. Okay.
Mm-hmm.
So actually, one can make a much better case with their data by not calculating the p-value, by looking at it from this point of view. Okay.
Definitely, yeah. Okay.
So as I said, you know, all I needed here, because it's just so black and white, is this concept that this is evidence in favor, evidence against, and in our case, I mean, this goes down to 0, and these go up to 1, right? In the end. So the case is so clear that we don't need to quantify, but there are ways of quantifying this and say, where you can say, I mean, how strong is this evidence? You compare the posterior with the prior. Okay, it's a little bit larger than the prior, so there's evidence, but it's not that strong. And here, relatively speaking, it's a little bit stronger. And this relatively speaking is reasonably strong evidence against the case 3, but it's not excluding the case 3, and so forth. So these things can be quantified, right? And so if you look at the these papers by Mike and his collaborators and students, you can read on that. Okay. Yeah, right. I just don't need to go into this right now.
Okay. Thank you.
Berge, can I ask a simple question? Or I mean, my impression is that the love to the p-value comes largely from the fact that it's a simple number that you can compare. And this 5%, wherever it comes from, is of course a choice. And if you want to compare, some other people want 5 standard deviations. So wouldn't it be nice to have a similar categorical cut for this Bayesian strategies, where you can say, well, is there a way to define such a number?
Well, I mean, first of all, this 5% threshold for p-values goes back to, I think, Fisher, right? The famous Fisher of the Fisher information and so forth, right? Who was sort of a pope in statistics, and he at one time says 5%, 1 in 20, right? But I mean, that's like the 1920s, 100 years ago. And so in those days, you simply did not have methods that could evaluate big chunks of data. But as I said, I mean, one of the efforts recently is to say that among statisticians is that we will now use threshold value which are 10 times smaller, 0.5% rather than 5%. So it's 1 in 200 rather than 1 in 20. But it's not so much this number that I'm criticizing. It's the general philosophy of the p-value and the general philosophy of these confidence intervals. So it's it really helps to understand this Jaynes example, right? So here you would calculate a p-value from this data, but it's clear that this what this 95% confidence interval that you report here does not contain the true value. The data tell you that it does not contain the true value, right?
Yes, of course. That's not my. I agree with your argument in toto. I just think maybe there's a possibility to derive something analogous to the p-value from the Bayesian statistics, and that you have a number that simple people who do pharmacological large experiments, for example, can simply look up and say, well, that this is 7 or whatever, and that's therefore okay. You see what I mean?
Yeah. So as I said,
application.
As I said, you can quantify how strong is the evidence, right? And then depending on the application, you can decide this is strong enough or not strong enough. And I don't know whether we need to have like a value like this 5% for the p or 0.5% for the p that is just dictated by some statistical society, right? I mean, in the end, it's up to you whether you consider the evidence strong or not strong. Okay, so fortunately for my talk today, I have this situation where there is no debate. Okay?
Sure.
But suppose you would have 0.8 here, and then for one of them, and 0.1 and 0.1 for the other two. Then you can say, well, you know, it looks like strong evidence, but the other ones are not really excluded. Okay, right? So I would say you evaluate the data and you just report these numbers and leave it to the reader to decide whether the reader finds the evidence strong enough or not strong enough. So it's a different matter if you are, you know, in a government office where you have to decide whether drugs do what they are supposed to do. You need some criteria that are probably decided by lawmakers and where you can defend in court. But here we are scientists, right? So you show me your data and I draw conclusions from it.
Okay, can I ask a question, Berge?
Yeah, sure.
Okay, so I'm changing a bit, I mean, the angle, okay? So I'm talking about, I mean, climate, global warming. The people are often publishing p-values, right?
Oh yeah.
So,
actually,
what is your conclusion about that?
Just yesterday, actually, I saw a paper about the efficiency of COVID vaccines and how it decreases over time. And the numbers were given. The numbers given were p-values and 95% confidence intervals. Okay, so when it comes to these numbers, there is a reasonable way of using them and an unreasonable way of using them. So let me just go back to the Jane's example. Okay. So if you look at this appendix, yeah, you will see that in addition to the standard confidence intervals, you can also be guided by the Bayesian reasoning and choose your confidence intervals differently, because the confidence intervals, that's not unique. Okay, how you construct them is not unique. Okay, whereas the smallest credible intervals from the Bayesian reasoning, there's no choice for you to make other than the choice of prior. Then the rest is dictated. Okay, whereas for the confidence intervals, you can use different constructions. And there is this famous statistician from MIT, I forgot the name right now, who once said, you know, that if you are good frequencies and you need to do this, you first look what the Bayesians do, yeah, and then you copy that and you use any justification that you can give. Okay. So one can actually construct confidence intervals here, which are guided by what we learn from the Bayesian method. And then in the end, these confidence intervals are quite similar to these credible intervals. Yeah. However, there is really a different meaning. Okay. So the credible interval, that says, if at 95%, it says that the true value is in this range with 95% probability. So if you have a confidence interval, and this is a 95% confidence interval, it does not have this meaning. It does not have the meaning that the true value is inside with a known probability. Okay. And this example is sort of telling it, because the true value is definitely outside. You can, you know that it is outside because the data tell you that it is outside. Nevertheless, this is a perfectly correctly constructed confidence interval from a standard set of confidence intervals. Actually, the kind of the standard construction that everybody would automatically use until you notice that it doesn't work. Actually, you can construct other examples. If you look at this appendix, if you have different data, then you may end up with a confidence interval that covers the whole range. Okay, so the true value is certainly inside, but again, you don't know anything specific. Okay, so I really like James's example because it shines light on this problem. Now you don't get this kind of insight if you look at the standard textbooks. I mean, like the ones that I have on shelf that you know are used for undergraduate statistics students, because the examples studied there with normal distributions and so forth, and these examples don't show these anomalies. So you may actually be misled into believing that if you have a confidence interval of 95%, I am confident that the true value is inside, okay, with a confidence of 95%. But that's not what these intervals mean. Okay. So it's a conceptual issue, really, more than you know, a calculational issue. Okay. Now I also have to say that when it comes to practical matters, it's usually much easier and less less involved. I mean, the CPU time that you use to evaluate the data, if you calculate p values or confidence intervals, is much less than when you calculate these credible intervals. Because for the Bayesian methods, let me just go back. We have to calculate these numbers. I mean, these integrals. Kind of lost now. Okay, so we have to calculate this number, this integral, in our case over an 8-dimensional space, right? And so we need Monte Carlo methods for that. We need reliable and efficient ways of sampling according to the distribution to determine the size and all that. So the numerical effort in the data evaluation is larger if you use the Bayesian methods, which is also the reason why historically they didn't play a big role until the computing power was available, right? So I mean, we just have this problem that we have to calculate this. Now, remember, this likelihood function is extremely strongly peaked, right? So if you want to sample from this kind of distribution, you need very good methods for doing that. Okay, because you have a distribution now which where almost all the probability is in a very narrow parameter range, and sampling reliably from such distributions is not an easy process. So it needs numerical methods that are sophisticated, much more than you need for calculating p-values, right? So I mean, people who do drug tests on patients in the medical school, they can calculate p-values, yeah. But I'm pretty sure they wouldn't have the skills to use these Bayesian methods. I don't want to say anything negative about our colleagues in medicine, but you know, they have different skill sets, right? Yeah. So I mean, the p-values are also popular because they're easy to calculate, so, right? And they are not meaningless, but one has to understand their meaning correctly. Right. So we're just, I mean, going back to the data I was looking at. I mean, for these three cases, the Vienna, Boulder, and Munich, we end up with having overwhelming evidence, clear evidence in favor of quantum mechanics and against local hidden variables. And even in the Delft experiment, which doesn't have a lot of data, we have very, very strong evidence in favor of quantum mechanics and against local hidden variables. But there are some residual probabilities for the local hidden variable case. But that's just because they don't have much data. Right? Any other questions?
Precisely, Berge. So just to just come to what you say. So how's your Bayesian statistic is functioning precisely where there is not a lot of data? Suppose that there's very few data, but for some reason they're spot at the right place somehow.
Yeah.
I mean, so I think if you have a p-value, the p-value will be large somehow because it reflects the fact that there is a pure number of data. But what about Bayesian?
Well, what I did not talk about is, but let me, since you're bringing this up, let me look at parameter estimation, right? So suppose you want to estimate a parameter from data, and you don't have a lot of data, yeah. Okay. So what the Bayesian method will give you is a credibility for smallest credible intervals for the data that you have at different levels of credibility. And then you can just say, I mean, I look at these intervals, and so I know that the true value is inside this interval with a certain probability. But if you want to have a high probability, your interval would just be large if you don't have a lot of data, right? So it's just a matter of being honest about what the data tell you. I mean, if you don't have a lot of data, the conclusions are not so sharp as if you have a lot of data, right? But you can still go through the analysis and assign credible intervals that make definite statements about the actual data. And you can go through the test. You can check whether your data is highly untypical or not. You can check whether there's a conflict between the data and the prior. So your prior is a formulation of your expectations. So suppose you expect a certain number to be between 10 and 20, and so you would assign a prior that is big in this range and not so big in other places, because I mean, these are your expectations, and the expectations are based on maybe yesterday's data or last year's data, right? And now you make observations and you find values which systematically are outside that region, right? In this case, you should be careful with the data evaluation because you have a conflict between your prior and the data. So your data either tells you that you didn't understand something about the data before, and that's why you had wrong expectations, or the data tell you that there's something wrong with your experiment. Okay, right? So if you have a conflict between the data and the prior, then there is no recipe of how to resolve the conflict, because it depends on the situation, right? It just tells you that you have to be careful in evaluating the data, right? Now, but of course, you can just have statistical outliers. I mean, you can toss a coin 10 times and get 10 heads. You know, although on average you would expect 5 heads and 5 tails, but for this run of 10 tosses, you get just 10 heads. That's not forbidden. Yeah, it's just data that are not as typical as other data. So in this case, you probably want to take more data before you start evaluating.
Okay. Any more questions? Okay, so if not, thank you again, Berge, for.
Yeah, thank you for having me.
Thank you for the talk, Berge. Have a nice evening. Goodbye, everybody.
Okay, bye-bye.
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 Bye-bye.